as we push deeper into space, and in situ resource utilization becomes more than just a buzzword. One big question starts to emerge. Can we really find all the raw materials we need to sustain ourselves, right there on the Moon, Mars, or asteroids? The short answer? Not quite. At least, not yet. In the early stages of space colonization and long-term habitation, we'll still need to bring some essential materials from Earth, either because they're too rare out there, or because they might not exist at all on our nearest celestial neighbors. That leads us to a critical question. What are we actually missing in space? Which elements might limit our ability to build, breathe, and survive off-world? Which resources are abundant? And which ones remain elusive? Let's dive into what we can't mine on the Moon, Mars, and asteroids for now, and why it matters for the future of human space exploration. While we often hear about how space is full of resources, the truth is more nuanced. Yes, there are plenty of raw materials scattered across the solar system, but only certain elements exist in quantities that are practical to extract and use. Let's begin with one of the most important industrial metals, copper. Copper is essential for building power systems, electronics, motors, and infrastructure. Its conductivity, malleability, and resistance to corrosion make it indispensable in modern technology. But here's the problem. Copper is almost non-existent on the Moon. While some asteroids may contain small amounts, and Mars could hold potential deposits linked to ancient volcanic or hydrothermal systems, nothing has been confirmed. No clear copper-rich formations have been identified yet in any extraterrestrial body within our reach. And without reliable access to copper, setting up efficient electrical systems off Earth becomes a major challenge. Next up, zinc. Zinc may not seem glamorous, but it plays a critical role in corrosion resistance, galvanization, and numerous industrial alloys. Unfortunately, zinc appears to be quite rare on the Moon as well. There's hope that Mars, thanks to its more diverse geological history, might host zinc-bearing mineral deposits, possibly remnants from past hydrothermal activity. But again, it's still speculation. The good news? In many engineering applications, zinc can be replaced. Alternatives exist, though they may come with trade-offs in cost, durability, or performance. Another metal on the missing list is lead. Lead is commonly used for radiation shielding, batteries, and certain construction materials. While it's not expected to be abundant in economically viable quantities on the Moon or Mars, there's an interesting twist. Scientists have speculated that lead might form snow-like surface deposits in the highland regions of Venus. But Venus is a no-go zone for mining. Its crushing atmospheric pressure, extreme heat hot enough to melt lead, and toxic clouds of sulfuric acid make any mining operation extremely dangerous with today's technology. Again, like zinc, lead has potential substitutes, but its scarcity could complicate early-stage habitat shielding or electronics manufacturing in space. Then there's the case of lithium, which has become one of the most talked about and strategically important metals on Earth in recent years, thanks to its key role in rechargeable batteries. On Earth, lithium is primarily extracted from either brine deposits, such as salt flats, or from pegmatitic rocks that form through complex geological processes. Neither of these environments are known to exist on the Moon. While some scientists believe Mars might harbor lithium-containing brines beneath its surface, this remains unverified, and if such deposits exist, they may be hard to access or process. So unless we develop alternative battery technologies or find viable substitutes, we'll likely need to bring lithium from Earth for the foreseeable future. And finally, we have the noble gases, elements like neon, krypton, and xenon. These gases are used in a surprising variety of ways, including ion propulsion systems spacecraft pressurization, specialized lighting, and cryogenic cooling. Unfortunately, they're nearly absent on bodies like the Moon or in asteroids, which lack substantial atmospheres and can't retain these lightweight, volatile elements. Mars has a thin atmosphere, but even there, noble gases exist only in trace amounts. Extracting them at scale would require processing vast quantities of atmospheric gas, likely making it inefficient with current tech. So what determines which elements are available and which are missing in space? The key lies in each celestial body's geological evolution. Earth is a geologically active planet. It has plate tectonics, volcanic activity, weathering, erosion, sedimentation, and hydrothermal systems. These dynamic processes help concentrate metals into localized, rich deposits, ones that are easy, or at least economical, to mine. On the Moon, however, things are very different. Its surface has been shaped mostly by meteorite impacts, not internal activity. It lacks plate tectonics and large-scale volcanism. As a result, even if valuable metals are technically present, they're dispersed thinly throughout the regolith, not clustered in rich veins or ore bodies. Asteroids face a similar issue. Most of them are small, primitive bodies, with no internal differentiation or active geology to drive the concentration of metals. Mars, on the other hand, is something of a middle ground. It's larger than the Moon and shows evidence of past volcanic activity, liquid water, and potentially hydrothermal systems, the very things that help form concentrated mineral deposits on Earth. That gives scientists hope that some Martian regions could hold valuable resources. But until we conduct on-site exploration and mapping, much of this remains theoretical. Another factor is atmosphere, or the lack thereof. Volatile elements and gases like hydrogen, nitrogen, or noble gases tend to escape into space if a planet lacks a thick protective atmosphere and a strong magnetic field. That's why the Moon and asteroids are practically devoid of these gases, and even Mars has lost most of them over time. That absence matters a lot. It complicates everything from producing breathable air to making fuel and cooling systems, pushing us to bring these ingredients from Earth or develop alternative technologies. Enough bad news. Let's look at the bright side. Space isn't barren. There are plenty of materials we can use. It just takes the right tools and strategies. Here's a rundown of elements and materials that are readily available or expected to be accessible off Earth. Oxygen. Despite what you might think, oxygen is one of the most abundant elements in space. It's locked up in oxides within rocks, dust, and water molecules. Through electrolysis or chemical reduction, we can extract oxygen from lunar regolith, Martian soil, or ice deposits. Iron and nickel. These metals are common in metallic asteroids, the Moon's basaltic plains, and Martian sediments. Iron-rich lunar dust could even be used in 3D printing structural components on the Moon. Mars, meanwhile, is famous for its iron oxide-rich surface, including those blueberry hematite nodules found by the Opportunity rover. Gold and platinum group elements. Though rare, these high-value elements are believed to exist in trace amounts in metal-rich asteroids. While heavy metals like iron and nickel might be used on-site, gold and PGEs could, at least in theory, be returned to Earth and sold, helping offset mission costs. Cobalt, found in some asteroid types, cobalt is essential for battery production, superalloys, and aerospace applications. Rare earth elements. These are crucial for modern electronics and advanced tech. Some asteroids and lunar areas show potential for REE concentrations, especially as byproducts of mining for other metals. Water, possibly the most valuable resource in space, found in shadowed craters on the Moon, C-type asteroids, and beneath the Martian surface. Water can be used for drinking, growing food, shielding radiation, and producing hydrogen-oxygen fuel. Magnesium, aluminum, and titanium. These are abundant in planetary crusts, including both the Moon and Mars. Lightweight yet strong, they're ideal for habitats, spacecraft frames, and structural materials. If some critical elements just aren't available in space, at least for now, how do we deal with that? There are 4 major strategies on the table. 1. Bringing materials from Earth. It's expensive, but sometimes it's the only option. High-priority elements like lithium, noble gases, or specialized alloys may need to be launched from Earth, at least until we find reliable sources elsewhere. 2. Finding substitutes. Necessity breeds innovation. For instance, aluminum can sometimes replace copper in electrical wiring, even if it's less efficient. We may develop alternative battery chemistries that don't rely on lithium or new construction techniques suited to space environments. 3. Recycling and repurposing. In space, waste is a resource. Metals, plastics, electronics, and even human waste could be broken down and reused. Closed-loop systems will be key to long-term survival and sustainability. 4. Planetary mineral exploration. As our space capabilities grow, we'll be able to survey and mine more locations, from larger asteroids to deeper Martian deposits. Future missions might even include robotic prospectors or AI-driven rovers seeking specific minerals. Building a long-term presence in space will require a deep understanding of local resources. And, just as importantly, a clear-eyed view of what's missing. We'll need to adapt, innovate, and rethink how we source and use materials. While Earth will remain a vital supply base for years to come, our ultimate goal is to thrive using space-based resources. As our technology improves and our exploration expands, we'll become better at finding, extracting, and transforming the materials scattered across our solar system. Until then, smart planning, creative engineering, and a little help from Earth will carry us through. And who knows? Maybe the next big mining rush won't happen in Nevada or the Congo, but deep within the asteroid belt or on Mars. What do you think? Let us know in the comments. Until next time, keep looking up.